So, hallo und herzlich willkommen zum heutigen OpenEMS Networking Friday. Heute zu Gast ist Herr Hendro Wicaksono. Er ist Dozent an der Jacobs University und sein Thema handelt heute von der semantischen Middleware. Bevor wir anfangen, noch kurz unser rechtlicher Hinweis. Diese Veranstaltung wird wieder aufgezeichnet und wird später auf unserem YouTube-Kanal zu sehen sein. Wenn Sie also gerne anonym bleiben möchten, dann bitte nur die Chat-Funktion benutzen, um mit uns zu kommunizieren. Dann würde ich auch schon das Wort weitergeben an Herrn Wicaksono. Danke, dass Sie heute hier sind.
Vielen Dank, Frau Simmel, für die Einladung. Ich mache heute auf Englisch, weil ich habe auch Kollegen aus England, Irland und auch Indonesien eingeladen. Ja. So, dann ich teile jetzt mein Bildschirm. Können Sie mein Bildschirm sehen? Oh, ja. Okay, kann ich nicht sehen in der Plattform. Okay, okay, ich mache auf Englisch jetzt. Good afternoon, everyone. So today I will give some presentations or share about our projects, also with currently with StormDAO. It's part of the project Delfine about the semantic middleware for the interoperability and explainability in demand response system that we developed. So before I start with the content, so I would like to introduce the Jacobs University where I'm working. So I'm currently a professor in industrial engineering at the Jacobs University Bremen since 2018. And Jacobs University Bremen is quite a young private university in Germany. So also small. We have only like around 1,500 students. But what is special in our university is that we have 110 students from, 110 nationalities among the students. And our university focus is more not only teaching, but also strong in research. Currently, our university is now joining with the Schaffhausen Institute of Technology. So it's a technology-based institute of technology from Switzerland, and it will change the color of our research in the direction of artificial intelligence with the different applications from life science, also in energy. So you can see just some figures about the research. So we quite focusing on the research, and there is some achievement. And I'm leading a research group called Intelligent Data Management in Industry 4.0. So basically, the research focus is on in the whole life cycle of data, from the data integration, the collection usually done by companies. We integrate the data on the semantic level using so-called ontology or semantic web technologies. And then we also do some machine learning to extract correlations and pattern from the data, and to do some forecasting and simulations, which then pass to some visualizations or some simulation softwares. So the application fields mostly in the energy systems or smart cities, and manufacturing, constructions, and also agriculture. So I will start now with the content of today's presentation, which is about the semantic middleware. So I will start with the background or motivation why we need demand response systems, and what is the role of the semantic middleware, where we can see it in the solution overview, and I will describe or explain the content of the semantic middleware, how is the architecture, and what's the interface, and how we build this middleware. And then I will also mention about another part of our research, which is the forecast or machine learning, and how this machine learning can be connected to semantic middleware, especially with the ontologies or knowledge graph as the future research. So now, as we know that Germany is now conducting the transition towards green energy. So, but it's not an easy task. There are some challenges faced in the transitions. So, for example, the renewable energy strongly depends on the availability of, or depending on strongly on the weather. For example, the availability of sunlight and also wind, and the storage for storing the energy to be used later. For example, we can capture the energy when the sunlight is has a high intensity, but to store the energy is quite expensive. And also we face the challenge in the distribution. So mostly of you can see here, the renewable energy resource concentrated in the north, but the consumer mostly in the south. So here then demand response plays the important roles to address the challenge. So what is demand response here? You can imagine that this yellow is the available energy in the grid because of the weather. For example, here because of the sunlight, you can see the peak of the available power is in the mid of the day. But for example, in this household, the consumption peak mostly at around 7 to 8 p.m. And demand response is how we can shift this consumption so that the consumer change their activities, and the activity that consumes more energy should be shifted to the time where the available energy or available renewable energy quite high. So that means shift this blue curve here, the red part here, to the green one, the green part. So, and how to do that? We need to play with the price, for example. So according to the study, it has quite a potential in 2030 about saving of 160 gigawatt and saving cost up to 50 billion euros. So with the demand response, we are now doing some kind of transformations in the relationships between generation and consumption side. So in current situation, or most of the situations, status quo is that the generations, for example, using coals or oils, is strongly directed by the consumption. That means we need to estimate how much the consumptions in some area or some district, some region, and then the number of or the amount of energy or electricity that should be provided depending on how much the consumption is. So, but now with the demand response, we can control the consumption so that it can match the availability of the generation. So that means we need to shift the consumption, we need to change the behavior of the consumption so that it matches the availability of generation. So an example of the implementation of demand response is to have time variable electricity tariff or dynamic tariff. That means, for example, if we have a lot of wind, a lot of available electricity, of course we need to see how much is the consumption. So that means here, if we have more electricity, means the electricity, the price will be cheaper. So that means if the price cheaper, people tend to consume their energy or shift their activity in the time when the electricity is cheaper. So according to some studies here in the US, so that there is a huge economic benefits of applying the demand response, especially here in industry, including manufacturing. So perhaps not the energy savings in gigawatt hours, but the peak saving is quite huge in industry comparing to residential, for example. So we with currently and some other partners here, you can see on the bottom here, we now are working on the project called Delfine, which want to address or implement the demand response systems for manufacturing consumer. So for example, here we have two manufacturing companies, Martek and Kaltenburger, and we have also Stadtwerke Trier as the electricity provider. So basically, this is the overview of the solutions. So based on the communications what we have here on one side is energy provider, on the other side is the manufacturing consumer, and we will develop semantic middleware that allow the data communications between the systems involved on both sides. So here we have some components, for example, on the energy provider, we need to have some kind of forecast of the energy generation that then will be used to calculate the dynamic price. The dynamic price here also needs some forecast of the consumption. So we did some kind of communication from manufacturing consumer to the energy provider here. And the semantic middleware is kind of facilitate this communication. So on the manufacturing consumer, the dynamic price will be communicated to the manufacturing consumer, and then the manufacturing consumer can plan their production accordingly to generate energy efficient production plan. So the system architecture of this Delfine project, so it's follow kind of edge and cloud architecture, and we also use OpenEMS in one of the component of the solutions. You can see here that the semantic middleware kind of the integration point of the solutions, where on the upper layer we have these different applications or modules from the tariff calculations, forecasting for both consumption and production. So you can see here, yellow is the consumer, and blue is the provider. And on the edge side, we have some metering systems. For example, on the consumption side, where we have where we integrate OpenEMS edge there, and we have also we need to also collect data from the productions, and also we get the data from the system that manage the power plants here. So basically, the forecastings will be done in kind of cloud, and also the semantic middleware is then as the communications and the common data vocabulary to allow the interoperability of different data involved in the solution. So now we move to semantic middleware. Here, the core of the semantic middleware is the technology called ontology. Ontology is kind of definitions of schema. First, it's a kind of metadata that formulated in form of graph, and it's quite common to be used as kind of vocabularies, a common schema. It was started in the medical sectors, and then from the European Union since 2010, it's transferred to the energy domain. And now a lot of projects using the ontology, especially for the energy domain that involve different data sources, different and heterogeneous data source. So now, because of the ontology is the one of the main component in the semantic middleware, we need to construct it. So why we need this ontology? Because in the semantic middleware, in the Delfine solutions, we require data from different sources, with the different formats. For example, productions data, and then sensor data, like energy consumptions, and energy generations data, and some other data such as weather and so on. So those data have different format, and we need to have some kind of common vocabularies and format for that to enable the data sharing between systems. And the ontology here provides a common vocabulary and schema in flexible way. So not fixed, but it can be extended depending on the use cases. Can be also just matter of extending the graph. So there is some already established approach to construct the ontology. First, we need to see. You can see here. There are 8 steps that we developed to construct the ontology based on some established method in this domain. So I will explain in the next slides. So the first step that we focus on is the step 1, 2, and 3, which is we need to gather the data requirements for the systems, for the developed systems, and then to find the domain of the ontology that can fulfill the requirement of the data, and then find the ontologies in that domain. Here, but before I go to that step, so you can see here the component of the semantic middleware. Here, for example, we use the existing ontologies. We don't construct the ontology from scratch, so we just reuse the existing one, which is already standard. Also, for example, OpenEDR for demand response, and SSN for representing the sensor data. And then we need to link them through so-called alignment, so resulting the final ontology or the final Delfine ontology that we will use as the core of the semantic middleware. And this is kind of define the vocabularies and schema of the whole data involved in our system. Then from the different data source, we need to develop some kind of mapping or use some mapping methods to map the columns in SQL, for example, or some part of JSON and so on here to this ontology. And then the result will be so-called knowledge graph. And knowledge graph is similar to what behind Google, where the semantics of the web, the whole web, is represented, and each of the node in the Google knowledge graph refers to some data source. We will do quite similar. And then we develop some kind of interface, so REST API that access the data, and this API then consumed or called by different applications of Delfine. For example, the calculations of price, calculation of electricity index, and so on. So this is the step 1, 2, 3, how we can run or get the ontologies, list the suitable ontology from the data requirements. So what we did is we have collected data requirements from the user, from the domain expert. So for each domain, for example, from the production and from the power generation. And then we identify there's different domains of ontology that we need to look at. So for example, here production, sensors, energy generations, and also demand response. And then look into each domain what ontology exists. Yeah, what ontology exists, and then we try to analyze them. And there is to do this, we get help with a portal called LOV, so link open vocabulary, so where we can search for some kind of domain keywords, and then we can get some examples of ontologies in that domain. So these ontologies, for example, SSN and SOSA, SAREF, and so on, already used by some projects in demand response on the household. And then the step 4 to 6, you can see here, 4 to 6 is to, after we find the ontology, we need to find the links between those ontology in order to fulfill the data requirement as a whole, not just piece of data requirement, but the whole data requirements. And then define links, and if necessary, we need to add some nodes. Development ontologies means here add some nodes if some nodes are missing and has not covered yet by existing ontologies. So that means we need to link these ontologies. Each of these ontologies is in a certain domain. For example, he's only in the sensor but not covering the production. Mason is only production but doesn't cover the energy, for example. And on the wind, only wind generation with power plant and so on, but it doesn't cover any sensors and productions. So that means we need to link them in order to have the ontology that cover the whole data requirements. And to link them, there is a different approach here. Link based on string, because each of the node has some kind of name and meaning. So we can match based on string, based on the words, a different approach to match them, or based on the lexical meaning, or based on some kind of thesaurus. And this is where the natural language processing approach plays into role. There's some existing solutions, LogMap and EML. We have started with it, but we want them to extend it so that there are different methods of linking is possible. And the result of the linking is our Delfine ontology that describe the schema of the whole data solution. So now, then the next step is step 7 is to map data source to ontology. So that means we have some original data source in CSV, SQL, or some JSON response. And then we need to map it to our resulting schema here. And then the result will be the knowledge graph that is stored in the Neo4j database. So we use OpenRefine, which is quite manual work. So, and now we want to make it automatic using OL ready. So like programming library in Python. And then this is the last part, because we also developed the machine learning for doing forecasting. So now how we can connect this forecasting and middleware, semantic middleware, especially the ontology part. So we developed different models for forecasting, neural network models, and do some experiments with it to do forecasts of wind and solar generations. And we also try Bayesian general additive model. So it's kind of forecast method developed by Facebook. And then how we can connect this machine learning method to our ontology. So the future research is actually to have some kind of how we usually machine learning is kind of black box. We just train the model using training data, and then get the model, and then test the model with some test data, and we can see the result, how accurate the model comparing the after the test. But what happened inside here, inside the machine learning, is not clear. So now it's quite important. It has been researched in the medical domain. So the ontology has a capability to describe some data in a formal way and in flexible way. So that means here we can relate, for example, two nodes, okay, machines with some kind of parameters of machines, for example, and with consumptions, for example. So we will use, or in the future, we plan to use the knowledge graph resulting from our alignment here. To first, we have already done it to describe the input data, and also describe the output, and also to explain for each node here. We're still researching it, how we can do it, but there's also already some work from different researchers in the medical domain. So we want to then adapt it and transfer the research here to energy domain. So that's actually my sharing today. So thank you also for your attention. So if you have questions, please, then I'm happy to answer.
Ja, vielen Dank für Ihren Vortrag heute. Ich glaube, wir haben keine Fragen bisher. Nee, bisher gibt es keine Fragen. Ja, der nächste Networking Friday ist am 8.10. Das Thema und der Referent steht auch schon. Das wird der Max Salomon sein, und er wird uns einen Vortrag halten über soziale, bezahlbare und nachhaltige Lebensgemeinschaften im Stadtraum. Ja, dann würde ich auch sagen, wenn niemand mehr Fragen hat, beenden wir den Networking Friday für heute, und jetzt im Anschluss gibt es noch die Möglichkeit, sich in die Social Lounge zu setzen zu Netzwerken. Dann wünsche ich Ihnen allen ein schönes Wochenende und bis zum nächsten Mal.
Vielen Dank, Prof.